Most of the things around me here are water resistant and dirt repellent. We also have stain resistant clothing, non-stick cookware, firefighting foams and coatings on food packagings and many other items, all of which owe their protection to man-made chemical compounds. They're known as perfluorinated compounds or PFCs, and we've been using them in all sorts of products for over 50 years. They're very effective, but there's a potential problem. They don't just stay in the product. PFCs have been detected all over the world in the air, water, soil, biota, blood and breast milk, so we need to monitor them. The most commonly known and persistent PFC is perfluorooctane sulfonate, or PFOS. It binds to proteins and accumulates in the blood, liver and gallbladder. So repeated exposure to it can cause health problems for humans. 177 countries from around the world have ratified a convention designed to protect human health and the environment from toxic and persistent chemicals. It's the Stockholm Convention on Persistent Organic Pollutants, or POPs, and one of the compounds on its list is PFOS. As a result, there's now a worldwide effort to ban its use. There is a global monitoring plan in place to keep track of the effectiveness of the convention. Countries are encouraged to collect human and environmental samples and monitor the concentrations of POPs over time. But not everyone is set up and ready to perform the necessary analyses. This training film produced for the Chemicals branch of the United Nations Environment Programme will help laboratories to analyse PFOS. We'll talk you through the various stages of the analysis of PFOS, PFOSA in air, mother's milk, water and serum, and also 4 precursor compounds, 2 FOSIS and 2 FOSAS in air. Before we get started, remember that Teflon contains PFCs, so don't use it during any of the extraction phases. We recommend that all Teflon tubings and materials in the ultra-pure water system be replaced. HPLC grade water is used in all solutions in water. The blank contamination of solvents and materials used during the analysis must also be tested to prove that they do not contain PFOS or any other PFC of interest. These should be cleaned if necessary and stored covered with aluminium foil. Remember, all steps may be slightly different in your laboratory, so always optimise and validate to suit your own setup. Let's begin with analysis in air. To collect PFOS compounds from air, we use polyurethane foams, puffs, that have been placed in a passive sampler for 3 months at an outdoor sampling location. These puffs are suitable for all of the target compounds, including the FOSAs and FOSIs, but not for the FTOHs. First, take the puff out of the sampler. And perform a Soxhlet extraction with methanol for 12 hours. You should add an internal standard of labelled PFC before the extraction. To concentrate the extract, we have a choice of using either a rotary evaporator or, as seen here, a Kuderner Danish. When the volume has dropped to 1 millilitre, filter the methanol extract through a 0.2 micrometer hydrophilic polypropylene filter, or GHP. Concentrate to 200 microlitres under a gentle stream of nitrogen.
Now add 100 microlitres of a mix of labelled PFC compounds as an injection standard and 300 microlitres of a 2 millimolar solution of ammonium acetate.
We're now ready for the final analysis using LC-MS-MS to identify and quantify them. But first, let's look at the extraction of PFCs from water, mother's milk and serum. The various stages are the same, but the volumes are different.
For milk, water and serum, after we've weighed our samples, we add a mix with labelled PFCs as an internal standard. We add 2 millilitres of 50% formic acid in water to the milk and serum samples and put them in an ultrasonic bath for 15 minutes. Then we put the extracts in a centrifuge at 3000 revolutions per minute for another 15 minutes, after which we do a solid phase extraction or SPE cleanup.
Water samples don't need to pass through the sonication and centrifugation stages, but may need to be filtered if they contain particles. They go straight to the SPE stage. For all samples, we use a special glass container connected to a vacuum pump. We put the 150 milligram wax cartridges on the valves on top of it.
To condition the SPE column, we add 4 millilitres of a solution of 0.1% ammonium hydroxide in methanol to the cartridges. When the solutions have sunk in completely, we add 4 millilitres of methanol. After the methanol's gone, we add 4 millilitres of ultra-pure water. For milk and serum, we change the amounts to 2 millilitres of 2% ammonium hydroxide in methanol, 2 millilitres of methanol and 2 millilitres of water. When this has also completely sunk in, we add the sample extracts. The flow rate is very important. The cartridges should be loaded with a flow rate with a maximum of 1 drop per second.
After the samples sunk in the SPE column, we'll wash the cartridges with a solution of 4 millilitres of sodium acetate pH4 for the water samples, 2 millilitres of a solution of sodium acetate pH4, followed by 2 millilitres of a solution of 40% methanol in water for the milk samples, and 2 millilitres of a solution of 40% methanol in water for the serum samples.
Next, we dry the cartridge by switching on the vacuum pump, without adding any solvents. The next phase is to extract the PFC compounds from the cartridges. For the water sample, we use 2 fractions. The first is extracted with 4 millilitres of methanol, and the second with 4 millilitres of a solution of 0.1% ammonium hydroxide in methanol. For the milk and serum samples, we use 1 millilitre of a solution of 2% ammonium hydroxide in methanol. We place the tube under a gentle stream of nitrogen, which allows the methanol to evaporate to dryness. Next, we add a volume of ammonium acetate solution to the milk extract and a mix of labelled PFC compounds to all 3 extracts as an injection standard, and put them in a centrifuge for centrifugation at 3000 revolutions per minute for 10 minutes.
We'll then transfer the upper liquid part, the supernatant, to an LC vial, and we're ready to perform the final analyses for all our samples, including the air sample, on an LC-MS-MS. But before we can do the actual analysis, the instrument needs to be prepared.
For the detection part, we strongly recommend the use of the triple quadrupole mass spectrometer, together with a negative electrospray ionisation. A time-of-flight mass spectrometer is another option, but unfortunately an ion trap mass spectrometer doesn't work well for PFOS. The mass spectrometer conditions need to be optimised for these compounds. We need to prevent any PFCs which may have originated in the HPLC system from interfering with your target compounds. So we put an extra column between the pump and the injector. There are several types of suitable analytical columns, but particularly recommended are C8 and fluorinated C8 columns. The solvents used for the separation and the gradient used depend on the type and size of analytical column. These need to be optimised before starting analysis. One of the mobile phase solvents, the ammonium formate solution, needs to be filtered before using it to prevent bacteria growing in the machine. The other mobile phase is 100% methanol.
The final task is to identify the compounds and quantify the concentration in the samples. To do this, we inject standard solutions containing different known concentrations to create a calibration curve. We use the areas of the peaks belonging to the right retention time and the M/Z transitions to establish the concentration of the PFCs. To guarantee correct results, we need to apply a number of quality control methods, such as use of certified analytical standards, use of certified reference materials and an internal reference material, plotting a QC chart, and including at least one blank in each sample series. It's important that we get correct statistics on the incidence of PFCs everywhere in our environment. By following these procedures in sequence, we can provide the data which will help us to accurately determine these POPs. It's an essential first step to manage the risks associated with these contaminants. It's an important job.